again start with modeling of DC servo motor part 2. In previous part we have seen the modeling of an armature controlled DC servo motor, and in that case we have keep a field current constant. But as you know, motor there are two current IA and IF, so we have keep field current constant. But suppose if you keep armature current constant, then in that case can we get any different model or can we get the same model? Therefore, here our main purpose is to develop the model of a servo motor when your armature current is constant. So, that means when the armature current is constant, what is the theta s by E of s? That is need to be determined. So, first of all we draw a circuit diagram of a field controlled DC servo motor. So, this is field resistance, this is LF, there is RF, then here is the applied voltage EF, and here is the armature part, and here current flowing is I, that need to be constant, and here we got torque TMT, motor torque. This, as I told, EF is for development of the flux, RF is a field resistance, LF is field inductance. Then this torque is produced, it has to drive, or the motor has to drive against the moment of inertia and the friction. Therefore, here is showing J and B. J is the moment of inertia and B is the friction. Here current flowing here IF. So, this is a circuit diagram of a field controlled DC servo motor. Now, we have to determine theta s, that is theta, here theta s by Es. So, how to get it? Here we have to develop theta s by actually EF of s, that is EF. So, how you do it? So, first of all we see here that the flux is produced because of this EF, that is the field current is produced, and because of this field current we will get the flux. Therefore, here we write this flux is proportional to field current. Therefore, this flux equal to Kf into If. So, this proportionality constant is replaced by like this. Then torque developed is proportional to your field current flux into armature current. Torque developed is proportional to flux into armature current, last time we have seen. So, again we can replace this by a constant K1 flux phi into armature current. Now, in this expression what we do, we replace this phi with this Kf into If. So, we write K1 then Kf to If into I. So, now we want the motor torque with respect to some parameters. So, in this case armature current is constant. So, this armature current is constant, this K1 is constant, this Kf is constant. Therefore, this motor torque we can write down as Kt dash into If. Now, with respect to torque the expression we have obtained. Now, how to handle other part of it? So, other part just we are observing, we are getting the part respect to Rf and Lf. So, this part we can solve, or this we have to solve, and here there is no need because here armature current is constant. If you see in a previous part, that is the armature control, DC servo motor, we have solved the armature circuit RA, LA like this. But here basically here we have this RF and LA because here field is varying, but here and in this case I is constant, therefore we have to apply Kirchhoff's law to this particular part. So we can write down this as LF di by dt plus field resistance RF, this is field resistance RF into IF equal to EF. EF is the applied voltage to this field part. Here also we applied, but this we are keeping constant. Now we have developed the circuit for this portion, then we have got the expression for motor torque, and here we will find one difference, there is no back EMF. If you see last time in a armature control there is a back EMF has come, but here there is no back EMF because here we are keeping armature current constant, therefore there is no back EMF. That means just the there is, we can consider here there is no controlling part. Then let us see what will happen afterward. So here we got expression like this. Now we see the expression for torque, that is the mechanical torque. So here we can write down J d square theta by dt square plus B d theta by dt equal to motor torque Kt dash into I, that is this is the thing but this. So we got the expression for this and expression for this, and this is another expression, but we have adjusted like this. So we have got these two equations. So everything, every part we have covered here, and now we have to develop a model that is theta s by EF. In case of your armature control, we have determined theta s by Es, because in this case we have applied input to the armature side, but here input is to the field's time, that is the important issues because that is varying. So whatever I explained, now again just see it. So here motor torque K1 Kf If into I, so Kt dash into If, so that means this we have got. Then about the field control circuit, EF LF di by dt into If into Rf, this part, and third part is torque equation Kt into If, that means this expression we have shown here again. So we have got equation in the time domain, so we want in S domain, therefore basically what we do, we apply Laplace transform. So we are applying Laplace transform of equation in 2 and 3, that is this is equation number 2 and this is equation number 3, we got like this. And now from this expression, this If of S is written like this, and now this expression of If of S in 4, replacing If of S in 4, this 4, so we got this result. Now what to do next? Now we have to simplify it. So here in order to simplification, the theta of S is taken common here, and afterward this theta S is written like this and EF like this and adjusted the variable like this, and from this we have got this expression. Then again this B and RF, this adjusted like this, and we have got this particular expression, that is LF by RF is replaced by this tau FC and J by B is by tau MS. So what is mean by this? So Km Kt dash BRF, so here this part, this Kt by Km is replaced by constant Km, that is called motor gain constant. Then here tau FC is replaced by LF by RF, that is called time constant of the field circuit. And again you see that in a time constant, what is time constant? Time required for the system to reach 63% of the value. So as the time constant is more, your system become little bit slow. If your time constant is less, your system is fast. You will find that the time constant in case of this field control is dependent upon LF and RF. So, normally the field winding resistance or inductance is more, field winding inductance is generally more, therefore, we will find that the time constant of the field circuit is quite more. Then about the mechanical time constant J by B. So, we will find that this system is working in an open loop because there is no BMK, there is no control. So, therefore, if you draw the block diagram of this, the block diagram of this you will get like this, that is here 1 upon LFS plus RF to IF of S KT dash divided by S Js plus B into theta of S, E of S. So, a behavior of this is as good as open loop, whereas in case of armature control we have got the closed loop. Again we will find that about a time constant. Now, we just see the difference between the armature control DC servo motor and field control DC servo motor. The first point, the transfer function model a position control servo motor can be reduced to second order in case of armature control DC servo motor, whereas the model of field control DC servo motor cannot reduce to second order. Why it is so? Because we see that in case of armature control DC servo motor, this is an armature inductance and that is very, very small. Therefore, that can be neglected, and therefore, because of that reduction we have got the model as a second order model, but whereas in case of field control motor this is not the possibility. We cannot reduce the field inductance to 0. Therefore, we can say that the model of an field control motor, particularly position control model, is always be a third order, whereas in case of armature control servo motor we can consider the model as a second order by reducing its inductance. Next, the maintaining a constant armature current, second point, the maintaining a constant armature current IA is more difficult than maintaining the field current IF because of the back EMF of the armature current. Although we got some advantage that we can reduce the model in case of armature, but as far as the armature current is concerned, it is difficult to control because here back EMF plays. As we change as the speed changes, the armature current changes. So, controlling of this back EMF is also very challenging. Therefore, this is one problem is that it is difficult to keep a constant armature current, whereas it is easier to keep a constant field current. So, this is the issue or the difference between the armature control and the field control. The third point, the stability of the field circuit is poorer to that of an armature controlled DC servo motor, and stability is very important issue in control engineering. So, the stability of state space, these things we will see in the next part, but here it is said that stability of the field circuit is poorer. Why it is so? We will find that system is very simple, there is even no closed loop, but it is said that stability of the field circuit is poorer to that of armature controlled DC servo motor. Why it is so? This we can easily see from the model itself. You will see that the armature control model, it can be reduced to second order, whereas field control model is always a third order. And you know that if all the coefficients are positive in the third order and in the second order, what about the effect of the stability? If you see it, if I am taking one example, 1 upon S plus A, S plus B, let us see K. This is GS, this is it in open loop plant, and now what about a closed loop? We can write down closed loop as 1 plus G of S. So, we will find that if you draw the root locus of this, let us say root locus, let us say it is minus A and this is at minus B. So, for second order system we will find that, let us say root locus means that locus of root or locus of closed loop characteristic equation when one of the variable or gain k varying from some 0 to maximum value or 0 to infinity, that part you might have studied in a classical control. So, here now I am drawing here the root locus for this was what happened, one root locus formed here, this is a pole and there are no zeros, it will start from here, one is going like this, other is going like this, so it is like this. So, for second order system the root locus like this, that is k equal to 0 and here k equals to infinity, here k equals to infinity. So, one root locus start from here, it will move like this, other root locus will move like this. So, this is an imaginary axis and we see that if the roots are lying on the right side of the S plane, system is always unstable, left hand side system is stable. So, we will find that for a second order system the root locus is like this, just and again showing here, that is one is here. So, one is root locus starting from here, this is a breakaway point, other is moving like this, other is moving like this, this is breakaway, same point. You can see the how to read my root locus from any of the book, but for this point explanation of root locus is important. So, here we will find that for second order system as we change k 0 to infinity, here k equal to 0 to infinity, the root locus always lies on the left hand side. Therefore, you know, you just see here your armature control motor, okay, is always a first order or even a second, we can say if you say the speed control motor is always a in terms of first order, or in case of the we can say the speed position control it becomes second order. Therefore, if you go for the third order you will find that the root locus is moving towards the right side of the S plane. That means, if I am taking the third order plant, let us say k s plus 1, s plus 2, s plus 3. So, I am showing the roots s equal to minus 1, another root s equals to minus 2 and here s equal to minus 3, s equal to minus 2, minus 1, these are 3 roots. So, in this case what will happen, the one root locus in this case if you see the root locus start from pole terminate into 0. So, here the root locus style like this and another is root locus like the real part, and here one root locus from here it will move like this, another will move like this. So, we will find that at some value of gain k equals some value, let us say here k equals to infinity, at some value of gain here system become unstable. But in second order system is always stable. So, here as you see that the field system, field control circuit is always a third order, whereas in case of armature control it is a second order. That is why as the order increases stability reduces. Therefore, here we will say that stability of the field circuit is poorer to that of an armature control DC servo motor. Then time constant is higher in the field control DC servo motor in comparison to armature control DC servo motor. We find that the time constant in case of field control DC motor servo motor depends upon LF. Therefore, as LF is normally high, therefore time constant is higher, that part we can say the system is little bit slow. Then other point, the field control motor is useful for small size motors and armature control motor is useful for large size motor. It is because you know in case of field control motor it is difficult to control the armature current, and therefore this is not so, therefore this type of design, field control design cannot be useful for high power application, whereas in case of armature control field current can be easily kept constant. Therefore, we can say that armature control servo motor can be useful for high power applications. Now, these are some references. Thank you.